My name is Stephan Harding. I'm an ecologist. I did a PhD at Oxford on the ecology of a small deer called the muntjac deer in southern England. And now I work at a college called Schumacher College, after E.F. Schumacher, the economist who wrote Small is Beautiful, where we look at the reasons for the ecological crisis and its resolutions. And one of the first people I met there was James Lovelock. He taught the first course on Gaia. And we became very good friends then, and I began to collaborate with him on some of his modelling of Gaia, and generally just thinking about Gaia and talking about Gaia. And so I've done quite a lot of work with him, and also a little bit with Lynn Margulis, who also was involved with the Gaia hypothesis early on, and Arne Næss here in Norway on deep ecology. It's a very gloomy picture. It doesn't look good at all. All sorts of things that shouldn't be increasing exponentially fast are. One of the most worrying is the loss of sea ice, which is happening as we speak. Of huge amounts of sea ice, both in the Arctic and the Antarctic, but particularly in the Arctic, disappearing much faster than anyone thought. But there are many other things that are going wrong with the Earth. For example, we're deforesting the Earth incredibly fast, particularly in the tropical regions. There's an exponential rate of tropical deforestation. There's huge amounts of water use. So we're now using, almost drying up rivers, like the Colorado River and other rivers around the world. We're consuming paper at an alarming rate. The number of cars, motor vehicles, are also increasing exponentially fast. I mean, the list just goes on and on and on. In fact, the International Biosphere Program, the IGBP, came up with a series of graphs which show a whole lot of very worrying parameters increasing exponentially fast. So it's a very bad situation. We really are in a crisis. And one thing I ought to mention, one bad thing I should mention, is the loss of biodiversity, which is also so severe now that scientists are talking about us being in the 6th greatest extinction spasm that the Earth has ever known. We're losing species probably 1,000 times faster than the natural background rate of species extinctions. I think if you don't get depressed, you need to see a therapist. I mean, on this issue. There's something wrong with you if you don't get depressed about this. You'll need help to work out why you're not depressed. And I think many people are, not enough people are depressed. I think many people are in denial, because our consumer culture just cocoons us, temporarily at least, from this knowledge and from these terrible things that are going to happen to us. Well, this is Jim Lovelock's great contribution to science, for which he definitely deserves about 10 Nobel Prizes. At least one, anyway. And that is that the Earth as a whole is a great system. Now, what do we mean by a system? It means that it's pretty obvious, really, that everything is interconnected. That the land, the oceans, the rocks, the atmosphere, and the living creatures are all connected in one great system. So that anything that happens to any part of the system will ramify through the whole and can shift it to new states, potentially. Well, if we lose the ice caps, then that warms the world, the planet, because you lose the bright ice cover which reflects solar energy back to space. So we get a warming of the planet as a whole. And if the warming becomes quite large, it will affect weather patterns and wind patterns, even as far down as the Amazon. And so the Amazon may receive less water from the Atlantic Ocean, in which case the Amazon will dry out and burn. And the burning of the Amazon will then release carbon dioxide gas to the atmosphere, which is in itself, as you know, a greenhouse gas, which warms the Earth, which will lead to even more loss of the ice further north, and possibly of not just the sea ice, but the ice caps. And so the whole thing becomes self-perpetuating. I don't know if Jim Lovelock said this, but his great insight about Gaia is that the Earth is a system, as I said, but there are two parts of it, in a sense. One is the living component of it, that's to say the sum of all life, the trees, the plants, the animals, the bacteria, terribly important, the fungi, and these other creatures called the protoctists, things like algae that we don't really think about very much. So that's the sum of all life. And they have massive impacts on the non-living components of the planet. That's to say, the atmosphere, the rocks, and the water. And this is a radical proposal. Before Lovelock, the conventional wisdom in science, which now no longer exists, I mean, Lovelock's ideas are now in mainstream science completely. But before Lovelock, the idea was that the living beings couldn't possibly affect water terribly much, or the rocks, or the atmosphere. They had to adapt to these things, but they couldn't really influence them very much. But Lovelock showed how, in fact, living beings do influence the atmosphere, rocks and water. For example, without any life, you can show that there would be no water now on the planet, because living beings, particularly bacteria, are able to keep water around on the planet. And without life, we wouldn't have many of the rocks that we now have. We probably wouldn't have large continents. And it's an amazing thing. We probably wouldn't have large continents. And certainly the atmosphere of the Earth would be nothing like the atmosphere now, which is a highly reactive atmosphere because of the presence of oxygen, which is a highly reactive gas produced by, or liberated by photosynthesis. If it weren't for life, our atmosphere would be like the atmosphere of Mars or Venus, largely carbon dioxide and at chemical equilibrium. So Lovelock says life radically affects and changes the water, the atmosphere, and the rocks, but then they feed back to influence which life forms can exist. So we have a feedback, you see. And he went further. He said something surprising emerges as a result of this relationship, and that is that the whole system, the whole Earth system, is able to regulate its surface conditions to within the narrow limits that life can tolerate over huge periods of time. And that's basically the Gaia Theory, if you like. This is a completely revolutionary insight in science, at least it was at the time. Now it's completely accepted in science that living beings have a massive influence on climate. They call themselves Earth system scientists, because Gaia has this unpleasant connotation of animism. And Gaia is a goddess, and you're not allowed to have gods and goddesses in science, even though scientists conveniently forget that all the other planets are named after gods and goddesses. But for some reason, we're not allowed to name the Earth after our own, very own Greek divinity of the Earth, ancient Greek divinity of the Earth. So Gaia is a dirty word in science, although that's changing a little bit. It's now taken as a bit of a joke. You can say Gaia, but no one really thinks it's Gaia. But if you talk about Earth system science, that's perfectly respectable. And life has a central role in the Earth as a system. That's completely accepted. Whether there's an inevitable tendency for self-regulation at the level of a planet when you get this interaction between life and the non-living component is still debated. Jim would say that it's inevitable. I guess he would. Many others disagree with that. So Jim developed a model with Andy Watson called Daisy World, which in part looks at the role of biodiversity on a planet. Anyway, it's a simple planetary system. It's a mathematical model in which you have a sun which increases its brightness as time goes by, much like our own sun has done. Then you have a planet which has severely simplified biodiversity. We may have 30 million species on our planet, maybe more. Say 30 million, there's an upper estimate. On Daisy World, Jim and Andy Watson placed two species. These were daisies, one kind with dark petals and one with light petals. And there were seeds of both of these daisies scattered around the soil of the planet. There were no clouds. And they both followed a similar growth response, a temperature response. So they would grow similarly according to temperature. There'd be an optimum temperature, and then if it got too hot, they would grow less, and if it was too cold, they would grow less. So it was a sort of bell-shaped response to temperature. Both of them are the identical bell-shaped response. And they set this thing running, and when the sun was small and not very bright, black daisies, dark daisies, sprouted all over the planet. and rapidly spread because they warmed themselves on the planet. And so we got an explosive positive feedback as black daisies took over the space. But then the sun got warmer, and it wasn't quite so advantageous to be a dark daisy, because now if you were dark you were warming yourself up slightly above the optimum. And so now there was a possibility for white daisies to survive. And they helped to cool themselves on the planet a bit more. And as the sun got brighter and brighter, we got more of a mixture of black and white daisies.
This is based purely on Darwinistic evolutionary principles?
Yeah, it is. The equations, well, the daisies compete for space. There's no actual competition function there, but they just compete for space. The ones that can produce more offspring take over more of the planet. So there's Darwinian competition. And then as the sun gets brighter and brighter and brighter, the black daisies begin to disappear because they warm themselves too much, and eventually we have a planet with only white daisies, so the planet becomes totally white. So during the history of the sun, during the time, the evolution of the sun from less bright to bright, the daisy world goes from black and then to dark grey, lighter grey, as we get more mixture of black and white daisies, and eventually as the sun gets really, really bright, it's completely white, with only white daisies. And then when the sun gets even brighter, daisy world can't regulate anymore, and the whole thing dies. Now that's the point. The point is what happens to the temperature of the planet overall during this whole time trajectory. And the extraordinary thing that they found, and this never ceases to surprise me, is that the temperature of the planet always remained slightly below the optimum for growth, despite changing populations of daisies, black and white daisies, and an ever-increasing solar output. In other words, there was a sort of emergent self-regulation which came out of these simple equations. It's absolutely stunning. And it became a kind of toy model or a toy demonstration for how the real Earth could work. And then one thing I did with Jim over several years was to explore the role of biodiversity in this model. So he did some of that himself, but I helped him by making food webs that were more or less complex, that had more or less interconnections between them.
So you explore what increased biodiversity would mean to the self-regulation?
Yeah, that's right. Yeah, biodiversity in the sense of more interrelationships amongst the species, because we had daisies, and then we had herbivores that were grazing the daisies. And we made the connections between the herbivores and the daisies either dense or not dense. So this is more about complexity of the ecosystem rather than the biodiversity. And we found that if you loosen the connections between the herbivores and the daisies, the whole regulation of temperature was much less effective, and it actually oscillated. And as the daisies and herbivores became more tightly coupled with each other, as the richness of interactions increased between the herbivores and the daisies, the regulation of temperature improved.
Biodiversity is actually important to maintain Earth's temperature?
Yeah, I would say that's my speculation, or our speculation. I'm not sure that we've got evidence for that scientifically. We do have evidence on a much smaller scale from some studies on European grasslands and grasslands in North America, that more species in these grasslands lead to better ecosystem functioning, such as nutrient cycling, drought resistance, pest resistance. That's very well established. The project is called the BioDepth Project, and they've got a very good extensive website which details the results. So we know that biodiversity, at least in these grasslands, can stabilize ecosystem functioning, and there's evidence from other small-scale experiments. But at the level of the Earth, it's a speculation to say that biodiversity increases the climate regulation abilities of the planet. So, but I think it does. I think but I can't back that up with data at the moment. To begin with, there was a huge resistance to it. This was back in the early 1970s, when Jim first published a paper, I think it was called Gaia as Seen Through the Atmosphere. And there was a terrible reaction, a very strong reaction against it. Now, why was that? It's interesting to speculate. Partly is because he used the name Gaia, which, as I said before, is not allowed in science. It's taboo to bring up the name of a goddess. You know, it seemed rather animistic. It seemed to propose that the Earth somehow had purposes of her own, that she had a sort of overall consciousness. It seemed rather New Agey, and they didn't like that. But there were other good reasons for criticizing the idea. One was that nobody could quite understand how this self-regulation could happen, because the conventional view was that the Earth is composed of lots of individually selfish organisms, all competing with each other, you know, in Darwinian ways. And how could all that Darwinian competition give rise to global-scale regulation? No one could see how that could happen. And it's a good point. We still can't see how it can happen. Not entirely, anyway. Still not clear how it works. The other criticism was that it implied some kind of mysterious consciousness at the level of the planet that was doing the regulating. It's called teleology, the notion that nature has purposes. And as we all know, nature is just meant to be this blind, dead, mechanical thing with no purpose whatsoever. So these were the criticisms that were levelled against the Gaia hypothesis, one philosophical, one more scientific.
So it was a kind of clash of worldviews, actually, yeah?
Yes, it was like a clash of worldviews, yeah. Because science had been progressing along, at least biology had, and geology, along very mechanistic lines for a long time. Not, of course, not physics. That changed with the quantum revolution in physics and with relativity. But in biology and geology and the other sciences, there was a very mechanistic outlook. Everything was dead. Everything was also fundamentally predictable. It was all the natural processes were linear in the sense that a given disturbance would produce a predictable effect. So a small disturbance would produce a small effect, a big disturbance would produce a big effect, and in principle it was thought that these effects could be understood and quantified and modelled mathematically. Suddenly Gaia theory was showing that, well, perhaps the Earth, in fact, is more like an organism than it is a mechanism. More like a giant physiology. And perhaps it's more non-linear than people felt comfortable with, that small disturbances might be able to propagate through the system and create large effects, as, of course, happens with our own physiology. So it was disturbing to scientists, I think, to think of the Earth as a kind of organism when they were used to thinking of it as a mechanism. But you can make a good case that bacteria are centrally involved in the movements of the continental plates. I can tell you the story of it if you like.
Yes, please.
Yeah, it's got to do with water, you see, because you have to have water for plate tectonics. The reason is that the water acts like a sort of lubricant.
Yes.
You know, as you probably know, part of the plate tectonics process is a rising up from the mid-oceanic ridges of a sort of semi-molten, very viscous rock from below, from deep below. It comes up, it solidifies and moves sideways. Yeah, and then eventually it sinks at the continental margins and goes back. Yeah, and as this plate of basalt rock moves sideways, it absorbs water. And there are certain chemicals in the rock that just love the oxygen in the water. And they want to get hold of that oxygen, and they do. They strip the oxygen out of the water, and that leaves free hydrogen. Now, hydrogen is so light that the Earth's gravitational field can't hold it down. And so it tries to escape back to space. where it really likes to be. You know, hydrogen likes to be in interstellar space. That's where it feels most comfortable. So it sort of tries to move out. And of course, if you lose all the hydrogen, which would eventually happen through this process and some others, but let's focus on this one, the Earth would lose its water because you have to have hydrogen to make water. The oxygen would be bound up in the rocks and the hydrogen would go off to space. And the Earth would dry out. But this doesn't happen because hydrogen is very important for metabolism. Living things need it to liberate energy from food molecules. And so bacteria in the sediments capture the hydrogen and use it to liberate energy. And by various means they recombine the hydrogen with the oxygen and reconstitute the water. So this means that thanks to the bacteria, water is maintained on the planet. And because there's water on the planet, plate tectonics can continue. And therefore the continents that ride on top of the basalt, seafloor basalt, like corks on top of water, those plates can then move around. And we can have mountain building and volcanoes and subduction zones, all because, well, in part because of what tiny little bacteria are doing down in the seabed sediments and capturing this hydrogen that would otherwise escape to space. This proves, it doesn't prove, but it demonstrates what Lynn Margulis has said, I think, several times, that it's the microbes that rule the world. Of course, unfortunately, now we are ruling the world, but it's really not our place to do that. It's the microbial realm that should be allowed to rule the world. For the last, say, 500 million years, they've been regulating. We've had multicellular life, like trees. Well, trees for maybe not 500 million years, but land plants. We've had recently great forests, and so now multicellular life has joined in the self-regulatory dance along with the bacteria. But when life first began, we think about 3,500 million years ago, basically all the regulation was down to the bacteria for perhaps 1,000 million years. And even after that, we only had unicellular or small nucleated organisms. So the microbes have been, let's call them microbes, have been involved with regulating the planet more or less on their own until the last 500 million years, for the huge bulk of Gaia's lifetime. But there have been crises. There have been, well, let's say radical shifts of state of the Earth. One of the most radical, you could say, was when life first appeared. There was must have been a radical shift in the atmosphere as the organisms began to draw down carbon dioxide for their photosynthesis and release methane from decomposition. So we probably had a methane-dominated atmosphere in the early days of the Earth. That was a quite radical shift. And then eventually there was another radical shift when oxygen began to become more abundant. And some people think around 2,000 or 2.6 billion years ago, suddenly oxygen became reasonably abundant in the atmosphere. And that caused a complete reorganization of the microbial biosphere, because quite a lot of the microbes didn't like oxygen and they had to go and hide down in the sediments. And other microbes could appear, the predatory microbes that used oxygen could appear on the surface. So a complete reorganization. So it's not as if the whole of Gaia has remained nice and smooth all the time and everything's been hunky-dory and without too many disturbances. There have been tremendous disturbances from within, created from within the system itself, by the system itself. Huge reorganizations, sometimes caused by internal factors, sometimes by external factors. And the regulation hasn't been perfect either. You know, it's wobbled around. Sometimes dangerously hot, sometimes dangerously cold. It's like almost like a semi-drunken Gaia walking on a tightrope. Sometimes almost falling off into heating and recovering a bit, and then almost falling off into cooling. And she's managed to keep this going for 3,500 million years. And of course you could think of us as the latest disturbance to her self-regulatory dance. And in order to regulate her temperature, Gaia has had to extract carbon dioxide from the atmosphere to compensate for the increasing brightness of the sun over geological time. If she hadn't done this, the Earth would be by now far too hot for life. And she's put the carbon in various places. Most of it has gone into chalk and limestone. And I can tell you about that process if you like. But
most people would probably think of coal and oil.
no, that's quite a small fraction of the carbon on the Earth. Most of it's coal and limestone. The next biggest...
chalk and limestone.
Sorry, what did I say? Chalk and limestone. Sorry, chalk and limestone. Yeah. The next biggest reservoir or box, if you like, or bank account or vault. But it's better to think of it as a kind of vault. It's as if she's trying to put the carbon in these vaults where it can be safely locked away out of the atmosphere. So the biggest is chalk and limestone. The second biggest is organic material dispersed through sedimentary rocks. And the fossil fuels is quite a tiny amount of that, compared to those two.
Why all the fuss then about us using oil and gas?
Because what Gaia has done is managed to bring down the carbon dioxide in the atmosphere to levels that are so low that plants can just about manage to live on it. Because, as you know, carbon is a food for plants. It's a gaseous food that they take in through little pores underneath their leaves, right? It's a gaseous food. So the Gaia has managed to keep the CO2, bring it down as low as she possibly can without killing off the plants, in the face of a very bright sun. Yeah. So if we then open up one of those vaults, take out stored carbon from the Earth's crust and burn it, we then return carbon dioxide to the atmosphere, and we make things much too hot. You could say it's good for the plants in the short term, which it probably is in the short term, but it makes the whole of Gaia so hot that it's a terrible danger for the whole biosphere. I'm not sure if I explained that, if you got the idea. Yeah? So it's terribly dangerous. As Gaia needed to keep carbon out of the atmosphere in the face of a bright sun, we're now returning it to the atmosphere, and so we're pushing the Earth into a hot state, which is extremely dangerous for us and for all other forms of life. So the last thing we should be doing is burning fossil fuels, or putting carbon into the atmosphere through any means whatsoever.
But don't the plants just take it out again? Why can't the algae and the plants take it out again?
Well, they can take out a certain amount, but they can't take it all, not at the rate that we're putting it out there. We're putting it out there at a phenomenally fast rate. Huge. I mean, it has happened before. About 55 million years ago, there was a massive release of carbon dioxide, long before we were around. And that was dealt with very slowly, and the sun was slightly less bright then. But at the moment, the biosphere, the ocean life and the land life, can absorb about half of what we emit. The rest of it stays in the atmosphere. And that half then, the half that remains in the atmosphere, then pushes the Earth into a warmer state, which begins to kill off the biosphere. For example, the algae don't like a warm ocean. They do better with a cold ocean. Because if the ocean gets too warm, you get a warm layer of water forming on the top. And nutrient-rich water from the sediments below can't reach the surface, and the algae starve to death. So as we warm the world by pumping greenhouse gases into its atmosphere, the oceans get warmer, the algae begin to die off, and so we lose two Gaian services that they give us, if you like. One is the absorption of carbon dioxide through photosynthesis, and the dumping of that carbon into the sediments at the bottom of the ocean. And the second is the production of clouds, because these algae emit gases which seed clouds, dense white clouds that cool the Earth.
You actually mean that when I'm looking at a cloud that's been made by algae and bacteria?
In part, yes. Not entirely. Some of it's seeded by dust. But yes, especially over the oceans, If you look at clouds over the oceans, they'll be, to a large extent, seeded by marine algae. They release these gases, a gas called dimethyl sulfide, which then reacts with oxygen and nitrogen in very complicated ways to give little particles of sulfur dioxide, sulfuric acid basically, that water just loves to condense around. It's like throwing breadcrumbs into a pond with fish. All the fish just coalesce around the breadcrumbs, and then the breadcrumbs are the particles of sulfur dioxide, the fish are water, bits of water. So you get these dense white clouds forming that cool the Earth. And as we warm the Earth, we lose these cooling services from the algae. And as we warm the Earth, of course, the plants begin to have a harder time as well. Water becomes harder for them to deal with. Sometimes, in some areas, if the weather patterns change, they suffer from water stress. And so they begin to die off, they burn, and they release more carbon to the atmosphere, which warms the Earth even further. It looks very bleak. I mean, as we were saying earlier, we're in the middle of a mass extinction right now. So we're losing species. It's like hemorrhaging species, as if someone's cut your jugular and blood's just pouring out. That's how we're losing species now on the planet. Unbelievably fast, as we both warm up the Earth and kill off species that way, and kill them directly by deforestation or overfishing. So the state of the Earth now is, the Earth is in a very bad state. If I would compare it to a social system, it would be like the collapse of the Roman Empire, perhaps. So the Earth is in a state of meltdown right now. It's like that very beautiful, complex configuration that she had evolved into when we first appeared on the Earth, with phenomenal, the highest levels of biodiversity ever seen on Earth. Tremendously complex and rich interactions in the tropical regions, with the northern oceanic regions full of cloud-seeding algae, with tremendous boreal forests and desert areas. All of that now is changing and melting down. We're losing that fantastic complexity. If you talk to some climate scientists, they will tell you that it's severe, but it's not apocalypse, that it's not. There are now inevitable changes, but we might be able to deal with them if we start reducing our carbon emissions now. So everyone agrees that it's a serious situation, but some people think that we can deal with it by reducing carbon, by, you know, these famous wedges by Sokolow, I think it is, that you just energy efficiency, carbon reduction measures, and we can get a grip on it now. There's still time to get a grip. Whereas others, like Jim Lovelock, as you know, say that it's already too late, because the changes now that have been set in place cannot be reversed. One example he gives is the loss of sea ice, particularly in the Arctic, which is disappearing catastrophically fast. And you can do a simple calculation that shows that just the sea that will be exposed to the sunlight, the dark sea exposed to the sunlight, will be in the Arctic Circle once the sea ice is gone. It will be enough to warm the Earth as much as we've warmed it already through our emissions of greenhouse gases, which is a lot. It's nearly 1 degree centigrade. So that's a huge amount. And once that starts, you see, it's a positive feedback. Once the Earth warms, these effects propagate around the entire system. The Amazon forests disappear, the boreal forests march northwards with their dark green leaves and warm the planet even further. Permafrost melts. So we end up in this, well, it's called a tipping point, or a series of tipping points, in which suddenly this whole system shifts from one steady state to another steady state incredibly fast, in a non-linear way, very, very quickly. You know, small effects you would have thought would have small consequences, but small effects suddenly propagate through the whole system and bring about catastrophic changes. Normally when we think about carbon or calcium or sulfur or oxygen, they seem to be rather distant, dead, mechanical objects, really, that we can't relate to at all. You know, very small, very insignificant individually, and
like billiard balls?
Yeah, like billiard balls that interact, but they don't not fundamentally change by their interactions. In other words, it's dead things. And it's very hard for us to relate to them, and therefore to the Earth, because they're so critical for the Earth, particularly carbon. So what I've done in my book, Animate Earth, is to speak of the chemical elements as personalities. And I've studied them very carefully, chemically, to see what those personalities might be like. Because for me, you see, everything is animate. There's nothing that's inanimate at all. Everything is animate. Everything is full of experience and sentience. Following Father Thomas Berry, I would say, like him, that the Earth is not a collection of objects, but a communion of subjects. So the old mechanistic worldview is that the world is a collection of objects, these billiard balls we talked of earlier. But what if the Earth is more like a communion of subjects? In other words, everything has subjectivity, even atoms and molecules, in which case carbon, oxygen, sulfur, nitrogen should all have their own personalities. And I tried to find out what those were by studying the properties of those elements. And I came to the conclusion that oxygen is like the passionate Italian of the chemical world, that it just loves to engage in fiery, passionate relationships with the other chemical elements. And that carbon is like the cooperative Swede of the chemical world. It just loves to make alliances with many other carbons to make huge long chains of carbon. We call these organic molecules. That calcium is a very dynamic princess that loves to get things going and get people excited in the chemical world. So that's what I've done in Animate Earth, and I've developed a version of one of the carbon cycles, the long-term carbon cycle in that book, which retells the cycle in more animistic language. Well, carbon and carbon dioxide, according to this story, become animated personalities. For example, for me, carbon is actually like a prince. I should have said a Swedish prince. A very cooperative Swedish prince. And he's in the atmosphere with his two oxygen courtiers in a carbon dioxide molecule. And he's dying, he's seen the world, seen everything. He's seen the insides of plants, he's been inside animals, in and out of the ocean many, many times. And he's dying for some kind of stability. Meanwhile, in certain rocks like granite and basalt, there lives, imprisoned, if you like, the calcium princess.
How does this relate to carbon emissions and the trouble we have now with fossil fuels?
Well, I suppose you could say that we're, as we said earlier, we're just liberating too much of the carbon that was kept out of the atmosphere by this Gaian process I'm describing. I can go into it if you like, or maybe you don't want me to.
So this is the way the Earth kind of removes carbon from the atmosphere?
Yes, this is the main way in which... Remember I said earlier that most of the carbon that was in the atmosphere is now in the form of limestone and chalk. This is the way that carbon finds its way into limestone and chalk. Because the chemical formula for chalk and limestone is Ca, calcium, C, carbon, O3. In English you call it calcium carbonate. So three of the chemical elements. The Ca is the princess, C, the carbon, is the prince, and oxygen is the passionate Italian. And they're all there together in this chalk. So the question is, how does the carbon get into the chalk? How does it get into this relationship with calcium and oxygen? Well, the story begins with the prince and his two courtiers zooming around in the atmosphere. And he's dying to find his calcium princess, but she is locked deep inside granite and basalt rocks in this crystalline lattice, like it's inside the granite castle, if you like. And so they need a priest to marry each other, and of course the priest is water, rainwater. But unlike human priest that goes home after the marriage, this chemical priest, the water, gets completely involved in the marriage. The three of them sort of get together. And what's released is hydrogen, little hydrogen beings that are so small they sneak their way into the granite castle. They go under doorways, so to speak, through little cracks under windows, and they find they sort of trip past the guards. You can imagine these huge, great chemical guards in the rock, guarding the rocky entrances to the castle. The hydrogen is so small, it's like a flea. It just goes between their feet, and they don't notice. But the hydrogen has got a positive charge, and this positive charge interferes with the electrical attractions in the rock, and it begins to dissolve, liberating the calcium, the princess. And she can then get together with carbon in the carbon dioxide. And this, very roughly speaking, is how the chalk is made. Actually, what's made is a solution of chalk, not solid chalk. And this solution of chalk is washed down to the rivers. This is the long-term carbon cycle, which regulates the Earth's temperature on geological timescales. And it's a process that will eventually remove the carbon dioxide that we've put into the atmosphere in about 200 to 300,000 years' time. So it's terribly important. It could be what's going to rescue Gaia in the long run.
So this Swedish prince is actually really needs to get into that rock.
Yeah, it needs to get into the rock. It's a very slow process, as I've just said. It takes 200 to 300,000 years. Slow from our point of view, but quite fast from Gaia's point of view. So once the prince and the princess have been washed by the rivers into the oceans, there, little marine algae, in fact, the same ones that produce the cloud-seeding gas, but also the corals or the crabs or any creatures that make chalky skeletons, absorb the chalk solution, make solid chalk, and when those beings die, their bodies sink to the bottom of the ocean, making vast deposits of chalk and limestone. And that's how the carbon prince gets out of the atmosphere. But then you might ask, what happens if this process goes on very effectively? Couldn't it cool the Earth to death? And that is indeed a great danger. We need just the right amount of carbon dioxide in the atmosphere. Too much and we boil to death, too little and we freeze to death, you see. Now this is it's amazing how Gaia has been able to know, so to speak, what the right amount of carbon dioxide is at any given moment. So, as you say, if too much is taken out, if too many of those carbon princes find themselves in the limestone chalk rock, the Earth will freeze to death. So why hasn't that happened? Well, because the great movements of the Earth's plates, plate tectonics that we referred to earlier, actually conspire to subduct some of that chalk and limestone deep beneath the continent, at the continental margin, because they lie on top of the basalt rock, which is coming up from below and moving sideways. Remember, we mentioned this earlier. That basalt rock carries on top of it the chalk and limestone. And when all of that meets the continent, it gets pushed down underneath. And there, the temperatures are so intense and the pressures are so intense that basically the chalk melts and the CO2, the carbon dioxide prince, returns to the atmosphere through volcanoes. And that saves the day. If it weren't for volcanoes, the carbon will end up at the bottom of the sea as chalk and limestone, and the Earth would freeze to death.
But how's the balance here, Harding? Is it when we release now fossil carbon atoms into the atmosphere, doesn't this increase the pace at which these Swedish princes you're talking about are sucked down into the ground?
It does, but remember, it's terribly slow. It's a terribly slow process. So imagine we were to capture a CO2 molecule in the room right now. You've got one here, you know, sort of thrumming in between my fingertips, right? Can you see it? Now I'm going to mark it with a little blue pen and then release it. Now what's it going to do? Well, it'll zoom around in the room for a while, and then when somebody opens the door, it'll find its way out of the door, and then eventually, when someone opens the window, it'll go into the air. And then it might go into a plant, where underneath, through a little pore on the underside of a leaf, and it might stay there for maybe a year or less, or it might stay there, might get into the wood, it might stay there for 300 years. But eventually it'll be returned to the atmosphere.